So before I can teach you how to solve a matrix equation, we have to learn one little matrix operation. If you recall back in the first chapter, what three things did you learn to do to a matrix? Multiply it, add it, subtract it. Did we divide them? No. You actually can't divide them, but you can do something that's similar to the division. You can use what's called an inverse. Because, for example, if I gave you 3, rather than dividing by 3, isn't it the same thing as multiplying it by a third? And you still, in this case, you get 1. So what we want to do is we want to find the inverse matrix, because multiplying by the inverse is the same essentially thing as dividing. So I teach you how to find the inverse matrix, and then we can use it to solve the problem, because we're going to need to divide here. So I'm actually going to first give you the kind of general formula for how you do this, and then we'll actually solve the problem. We are only going to learn to do this with 2x2s, by hand anyhow. Everything else, anything bigger, we'll do by calculator. Okay. So if I give you a nice little 2x2 matrix, and I want you to find the inverse. Okay. First of all, you have to learn the symbol in math. The symbol for inverse, we'll use it throughout the year on various things. Whenever you want to talk about an inverse, is a little -1 power. I wish they hadn't done that, because sometimes it means -1 exponent. Sometimes it means inverse. They've got that same notation, can mean two different things. Depends on what you're doing as to what it means. But I wish they had never used the same notation twice. So this is an inverse. That means the inverse of matrix A. Okay. To do it, you're going to have a fraction times a matrix. And the top of the fraction is always 1. The bottom of the fraction is what you already know. How do you calculate the determinant of this? What have you guys been doing to do these determinants? Yeah. A times D minus B times C. It's the same thing you already know. You do your little cross multiply thing and subtract, and that's what number goes on the bottom when you do an inverse. Okay. The numbers in the matrix, there's just a rule for how they switch around. The A and the D switch places. So D comes up to the top left corner, A goes down to the bottom right. The B and the C stay where they are, but they change their positive or negative sign. So I'm going to write it as -B and -C. They switch signs, but they don't move positions. That seems really weird that this should work, but it does. Now, actually, prove that to you. So let's just take an ordinary matrix here. Say I gave you the matrix 2, 5, -4, 9, and I said, find the inverse. You would go, oh, peachy, got this little formula right here, won't be a problem. Probably should have circled that formula. I think so. That's the important part. That's the key thing you got to remember. What now? Oh, you bet it's on the journal. It should be on the back. So, if I'm going to find the inverse, what's the formula say I should do? Okay, so I do 1 over, I write my fractions, and I do the determinant. I cross multiply the thing, which would be 18, yeah, because it's going to be minus the -20, which will make it plus. And we'll come back and add that, technically that, and that's 1/38. Now, what do you do to the numbers in the matrix? 9 and 2 switch. Yeah. The other two numbers stay put, but they change signs. So we'll have a -5 and a +4. And so if you take that times 1/38, you have your inverse matrix. And you're going, well, why would I care? I'll get to that one. You could distribute the 1/38 in there and make all of these fractions, but really, which is easier to read, 1/38 out front or all of those over 38? Yes. You don't want the fractions in there, so we just leave it that way. That's your inverse. So your first few problems today are just find the inverse. You go that far and you quit. Now, let me show you why an inverse works. Up here, when I took 3 times 1/3, if you take a number times its inverse, you always get 1. The same thing happens in matrix land. If I take that inverse we just found, and I take it times the original matrix, and the original matrix was 2, 5, -4, 9. If that's true, if this really is the inverse, when I multiply them, I should get the equivalent of a 1 in the land of matrices. And I also am doing this because we need to remember, how did you multiply matrices? Donna? Yeah. Row times column. Okay, the 138 we're leaving sitting out front to the very last step. You don't want to deal with that any earlier. So we're literally going to take row times column. So if I take the top row times the first column, first number times first number is 18, plus second number times second number would be 20. So that's going to add up to be 38. Is that a coincidence that we got 38? So, okay, take the top row times the second column. 9 times 5 is 45, plus -5 times 9. And so what do you get when you add those together? 45 plus -45 is 0. And then do the bottom row, same thing. Bottom row times first column, 8 plus -8, which would make a 0. And if I take bottom row times second column, 20 plus 18 would be 38. Now, what's going to happen if I take this 138 out front times every number in there? What do you get when you take 138 times 38? 1. And when you take it times 0, you'll get 0. And in the land of matrices, that's the equivalent of 1. When you have 1s down the diagonal and 0s everywhere else, and I'll write this in a bigger form. If I had a 4x4 matrix, it would look like this. If I have all 1s and 0s everywhere else, that's equivalent of multiplying by 1 in the matrix. So we just got 1. This inverse did cancel out the original matrix, and we're down to 1, which is pretty freaky that it works. I have no idea who figured this one out, but it works. For those of you who might be scholars-bull people, that's called the identity matrix, because if you multiply the matrix times that, you'll get the same matrix back that you started with. Because it really is like having a 1 in a matrix. That one would be an identity too. So you're going, what does this have to do with solving a system of equations? It's actually pretty amazing, but it has to do with it. So let's actually try a real life system here and figure out how do we turn these equations into what's called a matrix equation. Okay. Obviously, yes, you can still solve that by substitution, elimination, Kramer's rule, or graphing, but we're going to do a matrix equation. Okay. When you do a matrix equation, and I expect to see this first one set up, you're going to have a matrix times a tall, narrow matrix equals a matrix. In the first matrix, you're going to put your x and y coefficients. So I'm going to steal the 7 and the 3, the negative 11 and the 2. So obviously you still want to have your equations in standard form. That's really important. The second matrix will always be xy, because those are the variables you're solving for in this problem. Anybody want to guess what the last matrix is? 10 and 58, yes. Now the reason this is cool, if you do matrix multiplication, if you take the row times the column, 7 times x plus negative 11 times y, and since that's on the top row, it would equal the 10 on the top row. So it really is recreating this equation, only in matrix form. Ooh, that's pretty slick. So now what we want to do, we want to solve for x and y. Okay, you have this matrix times xy. In normal algebra, if you say I give you 4x equals 20, how do you solve for x? You divide by 4, or you could multiply by 1/4 if you wanted to multiply by the inverse. You would multiply both sides by 1/4. So in our case, we can't divide a matrix, but we can multiply by the inverse. So we're going to say, all right, I am going to multiply both sides by the inverse matrix. And right now I'm just going to write the symbol for inverse. I'm multiplying both sides by the inverse. That's the same thing as dividing over the 4. Because I know when I take the inverse times this matrix, if I took the inverse times its original matrix, what will happen? Yeah, I'll get the ones. I'll get the 1, 0, 0, 1. So essentially, it's like I'm getting 1 xy. I'm getting rid of the coefficient. I have just 1 x and y left. But here's where we actually have to do the math. I need to take the actual, figure out the inverse, and take it times 1058. Now, it matters which order you write these in, so that your rows and your columns line up when you do your multiplication. You have to write the inverse first. Inverse first. Remember that. Inverse first. Okay. So I'm actually going to do the little fraction thing first that we were just doing. And then I'm going to times it by the 1058 at the end, so that my matrix multiplication lines up right. Okay, how do I get to the bottom of the fraction? Yeah, do the cross multiply, so 14 minus negative 33, which is actually going to make that become a plus, and we have a lovely 1/47th, yeah. These rarely come out to nice fractions. Don't expect nice numbers here. Okay, now switch around the numbers. What goes in the matrix if I'm doing the inverse? If you're looking at your original matrix over here, the 2 and the 7 switch, positive 11, negative 33. Those change signs. Okay, so now I'm just copying this down onto the next line. Okay. All you have to do now is multiply your matrices and you'll have your answer. Because essentially, on the left side, you don't, actually after this point, you don't have to write the 1, 0, 0, 1. You've gotten x, y isolated. So we're solving for x and y here. When we get done, we're going to have the answers. Distribute 1/47 first or multiply the matrices first? Yeah, you don't want to distribute 1/47 to the last possible thing. So I need to multiply row times column. So if I go across the row and down the column, what will I get? 20 plus 11 times 58, that's 638. Nice number. And when I take the second row times the column, negative 3 times 10 will be Negative 30 plus 7 times 58. Give me 56. 406. And sometimes I look at these and think, oh, there's no way I'm going to get a nice answer. I got 147 sitting there. But amazingly, when I add that up, I'll get 658 and 376. Now, to times by 147 is the same thing as doing what? Just dividing by 47. So you're just going to divide 47 into both those numbers. And amazingly, this comes out nice. If you do 658 divided by 47, anybody want to guess? Bigger than the answers you've been getting. It goes in there 14 times. And then if you do 376 divided by 47, it goes in there 8 times. And so you just found out that x and y, x is 14, y is 8. And so if you want to write your answer still as an ordered pair, it's the point 14,8 is where those intersected. Look excited, guys. You could make sound. But it really does work. Pretty cool, actually. I want you to do another one just to make sure you've got the hang of it, and to show you that you can actually produce this pretty quickly once you don't have to go through all the details. Where am I? Oh, time-wise, I'm over.